Hi everyone. All right, so this is our first virtual lecture. Welcome to our virtual classroom. I'm sorry that we're not doing it live. I hope I'm still able to answer your questions live, but I promise I'm going to give you the same experience that you get in the classroom other than the component where you can ask questions there. And I know it's not ideal, but we're going to make the best of it. I know we're going to get by. So for this section, for trigonometric equations, we need to get re-familiar with our unit circle. So you should still have a unit circle. There's one online. You can print it off. You can use one of your old ones. We're going to go through and we're going to write the tangent values at each of the angles so that we have them for solving equations. I promise you this will be very nice later when you go to do some of these problems to have this in front of you with the tangent angles as well. So remember a few things. So sine, that's going to be your y value. Cosine, that's your x value. And then tangent was y over x. So looking at y over x, why don't we go ahead and, that's not my pointer. Why don't we go ahead and look at these guys first? So if x is 0, which it is here and here, then tangent is undefined because 1 over 0, that's not defined. So this is undefined, and this is undefined. Right? And then looking at these guys here, 0 and pi, if we do y over x, we have 0 over 1. And 0 over 1 is 0. Same with 0 over -1. Those are both 0. And then all we really need to do is get these remaining 3 angles in quadrant 1, and then we can figure out what sign they should be based on all students take calculus. So we're labeling the tangents. So all students take calculus. So tangent is going to be positive in, let's see if I can get a highlighter here. You know what, I'll mess around with that later. We're looking at where tangent is positive, so it's positive there and there, and then it's negative in these two quadrants, quadrant 2 and quadrant 4. So if I make myself a new thing, we're going to have positive tangent, negative, positive, negative. So I'm looking at putting negative signs for my tangents here, here, and here, as well as down here. And now all I have to do is the stuff in quadrant 1. So if we look at the pi over 3 angle, let me find a new color here. Let's go ahead and do purple. If we look at the pi over 3 angle, and we do y over x, that'll be root 3 over 2, all over 1/2. This will simplify down to root 3 over 1, which is just root 3. So this guy right here is root 3. I'm going to go ahead and fill that in on the remainder of my unit circle. Again, you're looking at the pi over 3 angles. Right. For pi over 4s, these ones are, that was an accident. For the pi over 4s, these ones are a lot nicer, right? Oh goodness, I don't know why that's happening. You have root 2 over 2, comma, root 2 over 2. So it's root 2 over 2 over root 2 over 2. This is just going to come out to be 1. So I have 1, -1, 1, -1. And then finally our pi over 6 angle. This one's going to be 1/2 over root 3 over 2, which simplifies down to 1 over root 3. Now, sorry about my computer chiming there. Let me go ahead and mute that. That didn't mute. I'm going to go ahead and leave this unrationalized. I'm going to leave it as 1 over root 3 for reasons. So You know me, I'm not a huge person for rationalizing in the first place, but I normally do with the special angles. But here I'm just going to leave it as 1 over root 3. Perfect. All right, so now we have our tangents filled out on our unit circle, and that'll be useful because we have sine, cosine, and tangent, which means we have all of their soulmates as well. All right, so let's go on to talking about solving some trigonometric equations. All right, so let's look at our first trigonometric equation. So something to point out, trigonometric equations are trigonometric equations because they have trig in them. So this equation I have down here, 2 cosine theta minus root 2 equals 0. It's a trigonometric equation because of the cosine theta, which might be obvious, but I'm going to say it anyway. And we're asked to find all solutions of this equation on the interval 0 to 2 pi. So 2 cosine theta minus root 2 equals 0. Much like with algebra, your goal is going to be getting that cosine theta by itself. So you can't get theta by itself right away, but we can get cosine theta by itself. So I'm going to start with adding the root 2 to both sides. Right? When we do that, we have 2 cosine theta equals root 2. To get the cosine theta by itself even more, we're going to divide by 2 on both sides. So we have cosine theta equals root 2 over 2. We want to figure out what theta equals. And we've been told that we're on the interval 0 to 2 pi. Cosine is the x value. There are 2 times on the unit circle where the x value is root 2 over 2. So let me just make a quick note here. Where on the unit circle is the x value root 2 over 2? Question mark. So coming back here, looking at the x values. So the x values are going to be positive in quadrants 1 and quadrant 4. And that looks to be the x value, root 2 over 2, here at pi over 4, and then again here at 7 pi over 4. So those are my answers. Now, you could check this out. You could use your calculator here to verify this. You could make sure your calculator is in radians mode to begin with. But let me get a new color. Let's do, I don't know, green. You could plug in pi over 4. So you could do 2 cosine of pi over 4 minus root 2 on your calculator and make sure that it equals 0. It will. So 2 cosine of pi over 4 minus root 2 is equal to 0. And then you could also do the same thing with the 7 pi over 4. With some of these more straightforward ones, that's not as necessary. However, as we get into some more complicated ones, that might be a useful strategy. So anyways, this is our answer right here. Pi over 4 and 7 pi over 4. So let's look at another problem. So find all solutions on 0 to 2 pi, and we have cotangent theta minus root 3 equals 0. All right, we want to get that cotan theta by itself. Not a big deal here. We're going to add root 3 to both sides. We get cotan theta equals root 3. Now, cotan theta is not one of our 3 main trig functions. However, cotan theta's soulmate, lover, partner in life is tangent. And we know that if, where's my red? Or let's do, sorry, I have to choose new colors now. It's really exciting and fun. Let's do some purple. If cotan theta is equal to root 3, that would mean we're looking for where tan theta is equal to 1 over root 3, because remember, they're reciprocals of one another. So where on the unit circle is tan theta equal to 1 over root 3? So coming back to our unit circle, we are looking for 1 over root 3. So we see that right here, positive 1 over root 3, and then positive 1 over root 3. So that's going to be at pi over 6 and 7 pi over 6. So theta equals pi over 6 and 7 pi over 6. And those are my answers there. So those were some more, let's call them basic problems. I'm going to call them basic because that's what Alex calls them. They're the more basic problems. But let's look at something that's a little less basic. So here we have 2 cosine theta plus root 3 times 2 sine theta minus root 3 is equal to 0. Now, I want you to think back to when you were in Math 126, or more aptly, Math 96, where you solved things like x plus 5 times 2x minus 1 equals 0. And when you solved something like this, you took each of these factors individually and set them equal to 0. So x plus 5 equals 0, subtract 5 on both sides, x equals negative 5. 2x minus 1 equals 0, 2x equals 1, x equals 1/2. So this is called the zero product property. Essentially, the zero product property says that if two things are multiplied together, so you have like A times B equals 0, that means that either A has to be 0, B has to be 0, or both of them have to be 0, because the only way you can multiply together to get to 0 is if one of the two is 0. We're going to use that same property to solve this equation here. We're going to take each of these factors and individually set them equal to 0. So I have 2 cosine theta plus root 3 equals 0. And then over here, we have 2 sine theta minus root 3 equals 0. So let's solve the first one. We'll start by subtracting root 3 on both sides. We now have 2 cosine theta equals negative root 3. Divide both sides by 2. And we get cosine theta equals negative root 3 over 2. For our second equation, we'll start by adding root 3 to both sides. 2 sine theta equals positive root 3. Divide by 2 on both sides. And you get sine theta equals root 3 over 2. So I'm going to be looking at my unit circle for 2 different things. The first time I go through, I'm looking for where cosine theta is equal to negative root 3 over 2. So where the x value of the coordinate point is negative root 3 over 2. And there's going to be 2 times that happens. So bringing it back over here, negative root 3 over 2 for the x coordinates, what we're looking for. So here we see negative root 3 over 2 for the x coordinate, and here. So that's 5 pi over 6 and 7 pi over 6. The next equation is asking where sine theta is equal to positive root 3 over 2. So sine theta is the y coordinate. It's going to be positive root 3 over 2 here and here. So that's pi over 3 and 2 pi over 3. And then you give all your answers as 1. So you don't need to necessarily put them in order. I'm just going to write 5 pi over 6, 7 pi over 6, pi over 3, and 2 pi over 3. And those are my answers to this equation. All right, so the problems that we've worked on, the equations that we've solved, have all asked to find solutions on the interval 0 to 2 pi. However, there are solutions to these equations that exist outside of that interval. In fact, there are infinitely many solutions that exist outside that interval. And a problem could ask you to find just simply all the solutions. So the way it's going to be worded on Alex, it'll say, find all solutions and write your answer in radians in terms of pi, and it will tell you some other stuff on there. This is asking for literally all solutions. Now, like I said, there are infinitely many solutions, so you're not really going to be able to find all of them and list them out. We're instead going to need to be a little bit more tricky than that. So let's just talk about how to solve these types of problems. Let me do a new fun color. So your first step is you're just going to treat it like it's a regular find the answers between 0 and 2 pi problem. That's where you're going to start. That's a little bit too bright on that color. Let's see. Make it a little darker. This is fun, right? So that's purple. Try again. Step 1. Find the solutions on the interval from 0 to 2 pi, which is what we've done all along. So we have 2 sine theta minus 1 equals 0. I am adding 1 to both sides. We get 2 sine theta equals 1. Divide both sides by 2. And you get sine theta equals 1/2. So if I go back to our unit circle, we're looking where sine theta is equal to 1/2. So where the y coordinate, because it's sine is y, where the y coordinate is 1/2. And that happens here at pi over 6 and also here at 5 pi over 6. But if you remember coterminal angles, the y value on the unit circle is going to be 1/2 if you added 2 pi to pi over 6. So at 13 pi over 6, it would be 1/2. At 25 pi over 6, it would be 1/2. And you can subtract multiples of 2 pi as well, and you would still land right here on the unit circle. That angle would produce the y value 1/2. And the same thing can be said over here if this 5 pi over 6. So what we're going to do, since we're allowed to add or subtract multiples of 2 pi, that gets written in a special way. Let me go ahead and just write down what it's going to look like. All right. So step 2 is add 2 pi k to each answer where k is an integer. Now, first of all, this is only for sine and cosine that you're adding 2 pi k. It'll be different for tangent, and I'll talk about that in a second. Oh goodness, I zoomed in. Scrolling is kind of what I wanted to do there. Okay. So in order to say, hey, it's totally fine if you add or subtract 2 pi's, we instead do this thing where we add 2 pi k, where k can be any integer. So that's saying that you could add any multiple of 2 pi or subtract any multiple of 2 pi because k can be a positive or negative number. The way that this gets written, so k is an integer, means so this is how it's written in math. This means k exists in the integers, or k is an element of the integers. So this is the mathematical notation for saying that k is an integer. This is important because this is what Alex is going to use. There is a button on Alex, and the button it says k pi, comma, k is an element of z. And so that's a button on Alex. So just so you know what that means, that's saying that k is an integer. So we found our 2 answers up here. We didn't write them down, to be pi over 6 and 5 pi over 6. So to give the answer for all solutions, we would take theta and we would write theta equals pi over 6 plus 2 pi k, where k is an integer. And also theta is equal to 5 pi over 6 plus 2 pi k, where k is an integer. And those are going to be my answers. Once again, the plus 2 pi k, that's just saying, hey, if you want to know all the solutions, here's 2 of them, and then just go ahead and add or subtract 2 pi from it, and that'll give you all the rest of the infinite solutions that there are. So for sine and cosine, as long as there's just a theta on the inside, if there's a 2 theta or a 3 theta on the inside, we'll talk more about those. If it's just a theta on the inside, for sine and cosine, you're going to find 2 answers and add 2 pi k to each of them. For tangent, you find 1 answer and add pi k to it, because tangent's period is pi. So why don't I write that down real quick? So if I go back to my unit circle real quick, because I want to talk about this, where's my pointer? I want to talk about this tangent thing. If I go back to my unit circle real quick, and let's just look at the value 1. So tangent's value is going to be 1 at pi over 4. And then directly across the circle, it's also 1. And if you went backwards, pi units, you'd also get to 1. So because tangent's period is pi, what you're going to notice is that the numbers match up directly across the circle from one another. So square root of 3, square root of 3, 1 over root 3, 1 over root 3, negative 1, negative 1, 0, 0. So you might ask yourself, well, why couldn't I just say pi over 4 plus 2 pi k and 5 pi over 4 plus 2 pi k? Which is a valid question. The answer is that it's redundant, and you are essentially giving one answer that is unnecessary at that point, because when I say pi over 4 plus pi k, I am including in it this guy over here. So you're writing 2 answers when you could just be writing 1. So you're going to want to write these as 1 answer. I have not double checked on Alex if it works if you do 2 answers, but I'm going to pause this and see if it does. Okay, so it does turn out that Alex will accept it if you do it as 2 different answers. But while, where was I? While doing that, while messing around on Alex just now, let me, I didn't leave it on there. Let me say a few things. So they have it as k pi. So their button actually says k pi, comma, k and z. I don't know if I said that before. So I always write mine as pi k, but they write theirs as k pi. It's the same thing. I believe, let me just click on a more practice. Yeah, so it'll always say just k pi. So you would want to put yourself a 2 in front of it if you're doing a sine or cosine problem. So it will, on the tangent problems, accept your answer if you write it as 2 separate answers, but it is redundant. You should really just write it as 1. Let's go ahead and do a tangent problem so you can kind of see how that would look. All right, so here is a tangent problem, a tangent equation, and we're asked to find all solutions, not just the ones that are in an interval. So we're going to start the same way that you start regardless, adding root 3 to both sides here. Then we have tan theta equals root 3. So we're looking for the places where tangent theta is equal to root 3. And once again, because this is tangent, we only need to find 1. So tangent is root 3 here at pi over 3. So theta would equal pi over 3. And then to get all solutions, we're adding plus pi k, where k is an integer. And that's our answer. So while Alex would be okay if you said theta equals pi over 3 plus 2 pi k and z. And then you also said theta equals, if we look back up here, 4 pi over 3. While you could write it as two answers and Alex would accept it based on the little experimenting I just did, it's unnecessary to write it this way, and if I were there to scold you, I would scold you if you wrote it this way. It really should be just written as one, because this is just being more complex than you need to be. It's putting more out there than needs to be put out there. As a small side note right now, so 5.1, 5.2, 5.3, and 5.5 are all grouped together right now. If you want to just get the 5.5 problems, you can go to the filter button, and then here's kind of the filtering terms that you can use. If you want to do the ones where you have to do the pi k, if you type in the word solving, that's going to give you all the ones where you have to find all the solutions. And that is the only thing that will come up if you type in solving as your keyword on Alex when you're in the 5.1, 5.2, 5.3, 5.5 section. Those will all just be the equations. The other one that you can find, the other word you can use to search is solutions. And this will give you all of the ones that are within an interval. So if you're wondering on how to search for that, that's how that works. So when you're on Alex, if you search solving, you'll get the all solutions ones. If you search for solutions, you'll get the solutions that are on the interval 0 to 2 pi. Let's go ahead and talk about some equations that involved squared trigonometry. So this one's on the interval 0 to 2 pi, and I see a cosine in there, so I think we're going to be having two solutions where we're adding 2 pi k each to them. However, we have an issue in that this is cosine squared and not just a regular cosine. And you do have two different options on how you deal with this. So we could do difference of squares. That would be my preference here. Difference O squares. Beautiful squiggly line. So if you have x squared minus 1, this can be factored into x plus 1, x minus 1. This is cosine squared minus 1, and that can be factored into cosine x plus 1, cosine x minus 1 equals 0. From here, we can split it into two different equations. So we have cosine x plus 1 equals 0. Cosine x equals -1. Over here, we have cosine x minus 1 equals 0. So cosine x equals 1. And cosine is the x value on the unit circle. So without even pulling out my unit circle, let's just kind of look at a rough sketch here. Cosine x is an x value. For it to be -1, we're talking about over here at pi. The times where cosine and sine are 1 are the kind of special things that don't follow along with this. So normally you're able to find two answers and add 2 pi k each to them. However, in the case of cosine or sine equaling 1 or -1, there's only one place on the unit circle that's going to happen. So here, between 0 and 2 pi. So the x coordinate is -1 at pi. And for the time where the x coordinate is 1, that's right here. Now, you have to be very careful. The way that this is written, there is a bracket on the 0 and there is a parenthesis on the 2 pi. That's because 0 and 2 pi are the same exact angle, so we can only include one of them. they have specifically excluded 2 pi. So the only one we can use there is 0. We can't use 2 pi because they've excluded 2 pi from the answers we can give. So x is equal to 0. So our two answers, x equals pi and 0. So that's doing it with difference of squares. The other method is the square root property. Square root property. This one I am more hesitant to even show you, especially since we're doing remote instruction right now. But because it's easy to go wrong here. But let's talk about it because it's worth mentioning. So we have cosine squared x minus 1 equals 0. We could add that 1 to the other side and have cosine squared x equals 1. Now, technically, you can take the square root of both sides as long as you put a plus or minus in front of them. So if I come in here and let's just write square root of cosine squared x equals, I am taking the square root of both sides, but I'm putting a plus or minus in front of the 1, the square root 1. Now taking the square root of something that's squared just kind of cancels out the square part, so you get cosine x instead of cosine squared equals plus or minus 1. And that splits into two different equations. Cosine x equals 1, cosine x equals negative 1. Here you're getting x equal to 0. Here you get x equal to pi. So you get the same answers, x equals 0 and pi. And the order does not matter. So let's look at another one that's similar to this problem. Once again, looking at the interval 0 to 2 pi, here we have 2 sine squared theta minus 3 sine theta plus 1 equals 0. Now, when you see something like this with a squared sine or cosine or squared trig in general, you could really think of it as 2x squared minus 3x plus 1 equals 0. And this could be factored. Now, this video is already over 30 minutes long, probably going to be closer to the 50-minute mark, hopefully not. I don't have time to go over how to factor. If you do not know how to factor, now is a good time to review that skill. But this is factored into x minus 1 to x minus 1. So I can use that same factorization, but instead of an x, I have a sine theta. So this factors into sine theta. If you can hear my dog growling, just ignore it. Sine theta minus 1 times 2 sine theta minus 1 equals 0. And then we can split these into two separate equations. Here we have sine theta minus 1 equal to 0. Sorry, my dog just needed to be let out. Sine theta minus 1 equals 0. And then sine theta equals 1. Once again, looking at the unit circle, sine is the y value, and the y value is only going to be 1 at one place. It's only going to be 1 here at pi over 2. So we have theta equal to pi over 2. That's the only place where it's 1. Now we have 2 sine theta minus 1 equals 0. 2 sine theta equals 1. Sine theta equals 1/2. So I'm starting to show less of that algebra. You've kind of seen it all along. So just trying to show a little bit less of it, get you used to doing more steps. So sine theta equals 1/2. We can go back to our unit circle. We're looking for where the y value is 1/2. So the y value is 1/2 here at pi over 6, and again here at 5 pi over 6. So we have theta equals pi over 6 and 5 pi over 6. So in total, our answers are theta equals pi over 2, pi over 6, and 5 pi over 6. So let's go ahead and look at another one where there's a square in it, but this one's a little bit different because previously we had that they were all sines. And now we're looking at this, and this has sine and cosine in it. So the way that you want to deal with this, let's get everything to one side first. So I can subtract the 1 and the cosine x on both sides, and I get sine squared x minus cosine x minus 1 is equal to 0. This is where you have to use a little bit of your creativity. Now, on ALEKS, when you're doing the topics, it's going to tell you that it's going to say using a Pythagorean identity. However, on the exam and on your quizzes, it's not going to tell you which trick you should be using. So you want to be looking out for this. I have one equation in mind that relates together sine and cosine. If you remember, it's the most important equation of all, and it's that sine squared x plus cosine squared x equals 1. So I could hypothetically get this sine squared x by itself by rearranging this equation. So subtracting the cosine squared x off both sides, this becomes sine squared x equals 1 minus cosine squared x. So sine squared x, same thing as this, I can replace sine squared x over here with 1 minus cosine squared x minus cosine x minus 1. The 1's are going to cancel because you'll have 1 minus 1, so those cancel. So now I have negative cosine squared x minus cosine x equals 0. Now, you could be tricky. So there's a lot of negatives here. I'm going to go ahead and be a little tricky here and multiply both sides by -1. If you do that, it just makes it so everything's positive because distributing the negative out, it makes both these guys positive, and 0 times -1 doesn't change anything. So I have cosine squared x, x minus cosine x, plus cosine x rather, equals 0. And now they both have a common factor of cosine x. So I can factor out cosine x, and I get cosine x plus 1. So that's by factoring it out. This is the same thing that would happen if you have x squared plus x equals 0, and you factor out an x. So that's the same type of factoring out that we're doing here. Now I'm going to split this into two equations. So the first factor is cosine x equals 0. So we are looking for where the x coordinate is 0 on the unit circle. Right? The x coordinate is 0. That's going to happen up here at pi over 2. That's where x is 0. And then down here at 3 pi over 2. So I get x equals pi over 2 and 3 pi over 2. For the next equation, cosine x plus 1 equals 0. So cosine x equals -1. Cosine x is going to be -1 in one place only. The only place where your x coordinate is going to be -1 is here at pi. So you have x equal to pi. So altogether, our answers are pi over 2, 3 pi over 2, and pi. So you just kind of want to be on the lookout for times where you can use these Pythagorean identities. Remember, there are a few of them, so maybe I'll just scroll down a bit. There's a few of them. Most importantly, sine squared x plus cosine squared x equals 1. But remember, we talked about that you could divide both sides by either sine or cosine squared and get a whole new equation. So if I divide by sine squared on both sides, then I get 1 plus cosine over sine. This part here, that's going to be cotangent squared. 1 plus cotangent squared x equals, and then 1 over sine. Sine's soulmate and partner in life is cosecant. So this is going to be cosecant squared x. So likewise, if I, instead of doing this by sine squared x, divided both sides by cosine squared x. Instead, you'd have, so sine over cosine, that's going to be tangent squared. So tangent squared x plus 1 equals secant squared x. So there are your three Pythagorean, let's see if I can erase this gently. Yay. There are your three Pythagorean identities that you want to use if you come to a place where there's a squared trig and a different trig function too. So if this were sine squared and this were sine, that would be fine. We could just move it over and factor. The problem was that this was sine and this was cosine. So that's why we had to adapt. All right, I promise that after this example, there's only one other example that I want to do. Maybe two. I might be lying. There might be two. But we're getting close is what I'm trying to say. I know there's been a lot of examples, but this is a heavy section, and this is a section that is very important going forward in your calculus career. You definitely need to know how to solve trigonometric equations. So looking at this one, we have sine 2x plus cosine x equals 0. This is a weird one because, once again, there's sine and cosine here. If you see a sine 2x here, this might be telling us, hey, we have a formula for sine 2x that we could replace here, and that might make it a little bit better. Sometimes not, but we could at least try, right? So let's go ahead and let me write down the formula for that. So the double angle formula for sine, so sine of 2x, that formula is 2 sine x cosine x, just to make it beautiful. So I'm going to replace sine 2x with 2 sine x cosine x, and then I will leave the cosine x alone, which you then might say to me, well, did you really solve any problems because now there's sines and cosines still? And I would argue that yes, I have solved a problem because now they both have a cosine x in common, and I can pull that cosine x out front. So I have cosine x times 2 sine x plus 1 because I factored out that cosine x. And now I can set each of these factors equal to 0. So cosine x equals 0. Once again, remember looking at your unit circle, the x-coordinate is 0 up and down, so at pi over 2 and 3 pi over 2. So, oops. X equals pi over 2, comma 3 pi over 2. And then over here, 2 sine x plus 1 equals 0. So 2 sine x is equal to negative 1. Sine x is equal to negative 1/2. So we're looking for the y-coordinate to be negative 1/2. Coming back here, the y-coordinate is negative 1/2 at 7 pi over 6 and at 11 pi over 6. So x is equal to 7 pi over 6 and 11 pi over 6. So putting all those answers together, x is equal to pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. And those are your answers. All right, so I'm going to do this problem and one more after it, and that's all, I promise. So let's look at this guy. We have 2 of sine of 2x over 3 minus root 2 is equal to 0. When you have stuff on the inside here, things are a little bit weird. Now, I don't have to worry about using a double angle formula or anything because it's just sine in here, and plus it's not even like we have a double angle, it's 2/3 on the inside. But we only have one trig function, so we should be fine. We're going to start by solving it the way that we normally would. So adding the root 2 to both sides, you get 2 sine, and I'll leave the inside part alone, 2x over 3, equals root 2. And I'll divide both sides by 2. So I have sine of 2x over 3 equals root 2 over 2. Now, if we had sine theta equals root 2 over 2, coming back to our unit circle where the y value is root 2 over 2. That's going to happen at 3 pi over 4 and pi over 4. So if we just had sine theta equals root 2 over 2, we'd have pi over 4 and 3 pi over 4. However, that's not what we have. We have instead this 2x over 3 in the inside. But if you could imagine, if I just erase the theta part and put in a 2x over 3, these equations would be similar, right? Let me undo that and leave it back as a theta. All right, so what we're going to do, we're going to kind of set this up similarly. We have 2x over 3, instead of saying theta equals, we'll say 2x over 3 equals, not root 2, equals pi over 4 plus 2 pi k. And then also we have 2x over 3 equals 3 pi over 4 plus 2 pi k. Now, we are trying to get x by itself because solving means solving for x. So you just have to do something a little bit tricky here to get x by itself. Let me scroll down a little bit. I can multiply both sides by the reciprocal. So if you have 2x over 3, this is the same thing as 2/3 x. I guess we could do this in 2 steps. Instead of multiplying by the reciprocal, I'm going to take myself back. Why don't we just do this in 2 steps? The first step, we're going to multiply both sides by 3 because that will cancel the 3's here. So we can distribute the 3 out. So here we have 2x equals 3 pi over 4 plus 6 pi k. And then to get the x by itself, we'll divide everything by 2. So the 2's here cancel. You get x equals 3 pi over 8 plus 3 pi k. So that's going to be one of our answers. Over here on the other side, we're going to do the same thing, but I'll do the reciprocal way of doing this. So this is one way of solving when you have a fraction over here, and then I'll talk about using the reciprocal over here. So if you have 2x over 3, this is the same thing as 2/3 x. To get rid of the 2/3, you can multiply by the reciprocal, which is 3/2, because it would cancel everything and you would just get x by itself. So I'm going to multiply by 3/2 on both sides. Once again, over here, 2's cancel, 3's cancel. You get x equals 9 pi over 8 plus, now you could do it in your calculator, but 3/2 times 2, the 2's would cancel, and so you would just get a 3 up there. So plus 3 pi k. And those are your two answers. So 3 pi over 8 plus 3 pi k and 9 pi over 8 plus 3 pi k. And again, that was because it wanted it in terms of pi. It wanted, thought I had a pointer. It wanted all solutions. On Alex, it'll automatically put in the k as an integer thing. But that's what you do if there's something on the inside here. So you only have to worry about messing with it after the 2 pi k if there's a number on the inside there. So let's look at something similar but different. We're looking at finding solutions on 0 to 2 pi, and we have the formula sine 2x plus 1 equals 0. Your first thought might be to say, well, I have a double angle formula for sine, so maybe I'll do 2 sine x cosine x, that's the formula for sine of 2x, that's the double angle formula, plus 1 equals 0, but this isn't going to really get you anywhere, right? Because I don't know how to solve for x after this because I cannot isolate x. So that's not quite going to work here. Instead, we're going to actually solve this the same way that we did, over here. We're going to get down to this point here, and we're going to have k's in our answer, and then we're going to come back for real answers. So we're going to get k answers first. And the reason for this is because there's a number on the inside here. So moving the 1 over, we have sine of 2x equals -1. And looking at the unit circle, the y value is -1 down here at 3 pi over 2. So normally we would say theta equals 3 pi over 2 plus 2 pi k. But here we're going to say 2x equals 3 pi over 2 plus 2 pi k. To get the the x by itself, we're going to divide everything by 2. We get x equals 3 pi over 4 plus pi k. Now, you might be saying to me, okay, that doesn't really help me because we're looking for just answers on the interval here. We don't need this pi k thing. And you'd be right. So k can be any number. And what we're going to start to do is we're going to start plugging in numbers for k starting at 0 and going upwards until we exit this 0 to 2 pi range. Now, notice that we have a 4 in our denominator here. I'm going to go ahead and rewrite this as x equals 3 pi over 4 plus 4 pi k over 4. So I'm writing it with the denominator 4. And then I'm also going to come up to my interval and write my interval in terms of pi over 4s. So this is like 0 pi over 4, comma, and then 8 pi over 4. So anything that's greater than 8 pi over 4, we're not going to use as an answer. So we start with k equals 0. I'm plugging in k equal to 0 for this equation right down here. So x is equal to 3 pi over 4 plus 4 pi times 0 over 4. We get 3 pi over 4 plus 0 over 4. We could say 0 pi if it makes you happy. This is just going to be 3 pi over 4. So that's going to be one of our answers, 3 pi over 4. All right. This is not outside of our interval yet, so I'm going to keep trying. I'm going to go ahead and try k equals 1. So you just increment by 1. And now you're plugging in 1. So you have x equals 3 pi over 4 plus 4 pi times 1 over 4. Scroll a little. So I have 3 pi over 4 plus 4 pi over 4, which gives me 7 pi over 4. Okay. That's still within our interval, so now we'll try k equal to 2. So x equals 3 pi over 4 plus 4 pi times 2 this time, because k is 2, over 4. We get 3 pi over 4 plus 8 pi over 4. And that's going to give me 11 pi over 4, which, if we look at our interval is from 0 to 8 pi over 4. So 11 pi over 4 is outside the interval, so we won't take him as an answer. But something I wanted you to notice here. So notice that each time we were adding 4 pi in the numerator here. So to get from 3 pi over 4 to 7 pi over 4, when we incremented k by 1, when we went from 0 to 1 here, we ended up adding a 4 pi to the numerator. So 3 pi plus 4 pi is 7 pi. That's why we have 7 pi over 4. Down here, we would have added another 4 pi. So 7 pi plus 4 pi is 11 pi over 4. So that's kind of a faster way to do that math, is whatever you have here, if you just ignore the k, you can just be adding multiples of this guy over here, and that will work. So our two answers here, see if I can scroll this thing back. Our two answers for this problem are going to be x equals 3 pi over 4 and 7 pi over 4. And that's that. So in general, the bigger the number on the inside, the more answers you'll have over here, and the smaller the number on the inside, the less answers. So if this were x over 2, for example, you're going to have even less answers. Again, the only time you plug in k values is a very specific situation where you have this 0 to 2 pi, and there's a number inside of your sine or cosine or tangent, or any of the trig functions, where using a double angle formula isn't useful. So I know this was really long. I'm certain it's close to the hour mark, but you guys are going to do great. Keep it up. I'll be back with another video soon. If you have questions, please feel comfortable asking. Let me talk. Please feel free to email me with whatever questions you have. I am happy to answer them. Hope you guys are staying safe and staying selfie. I can't talk. Stay healthy, guys, and talk better than I do. All right, bye.